Okay, so we were having some difficulties connecting to the network for the live streaming, so we'll just upload this video later. Okay, but today we're going to go ahead and just talk about the real-time rendering. So we were talking about the gbuffer. Essentially the gbuffer is just kind of one step in the process for deferred shading, and the other approach is monolithic. It's kind of like a monolithic approach. In other words, just do everything with one shader. So while I guess the disadvantage of doing the deferred shading is you have to do it in two steps. You have to actually render it to a separate memory buffer or texture map. And then the second step is then you use that texture map as an input for the shading part, and then you can kind of go through each light and kind of calculate the contribution there. So to make it simple, we're talking about the gbuffer, but what we really mean is like, okay, what do you generate if you're going to go that route? So normals, colors, that type of thing, and then later we do the shading part. So technically what I'm going to show you today is like this monolithic shader where we calculate all the values that we need, and then we can we'll do a second part where we pretend that we've already kind of written to the or that we've written to and we're reading from the gbuffer, and then actually do the shading part. So let's see here. Okay, so right now we have the teapot model, and we can do the normals, right? So we're getting we had a special way of like calculating the color. So we're going to go over here to the let's see which shader we're using. So go up here real quick and find out what we loaded. Oh yeah. Yeah. So over here, so in our app, right, we have our constructor, and we're going to go ahead and display a gbuffer. So what we can do is we can request a mesh. So the Xfer library has a class called meshes, and we can call the load method and just say we're going to call it teapot, and then this is the URL to load it at. Okay, we could also, I don't know if I have the bunny model in there also. I think I put some different ones. So yeah, there's a box, a bunny. So if I load the bunny one, oops. When this reloads, it'll have a different mesh. Okay, so there's the Stanford bunny. So he's kind of there at the bottom. So there's that one. We also have the dragon model. And these are very popular 3D models to test different things with. So there's the dragon model. At some point, I'm going to scale that teapot so it's the right size. I just haven't done it yet. Okay, and then there's the Mitsuba model. And Mitsuba is it's a path tracer that this particular model has kind of become famous for. So let's see, maybe we could look it up. So there's that model. The other option for me to here is to just use my phone for the internet, since the main one's not working. Okay. So Mitsuba is it's a path tracing. It kind of got its start similar to the book physically based rendering, and they wrote a thing called PBRT, and so it's a physically based renderer from Wenzel Jacob, and he's done a lot of research in terms of renderers and all that. But he has this particular 3D model that has been, where is it? Let's see what these are. Anytime you see this box with the light on top, it's called the Cornell box. This is another popular from Cornell University. So they did a lot of work trying to simulate. So important they even have like a Wikipedia page on it. So basically just trying to do a test setup for path tracers. So let's see if we can zoom. So normally it's got these two boxes in there, a red wall, a green wall, and then a light at the very top. And the idea is this is a way for testing rendering algorithms, see how accurate they are. Because it's very fast scene. There's just like a handful of polygons. So this is kind of in the same league as the teapot, the bunny, the dragon. There's another, when you want to do anything more complicated than that, I guess they did this back in 1984. And so they actually made a actual physical box and then they photographed it. So then they could compare their readings with the, whatever their rendering was with the actual box. So that's why it's kind of popular. Another one that's popular is the Sponza Atrium. So you can see the teapot, the Stanford Dragon, but the Sponza Atrium is also really popular. I like this one a lot just because it looks, it's based off this place in Croatia. So this is what it looks like for real. This is what it looks like for real. And then there is, somebody had made a 3D model of it. Oops. I don't know if this is a real picture or not. Let's see. Yeah, so somebody had made a 3D model based off this one, and they use it all the time for testing physically based rendering and stuff. So yeah, so there's different standard ways of testing things. Yeah, this is because these, I know for sure that I guess I'm just familiar with how it looks, but I'm pretty sure they don't have grass growing in the middle of it and statues, and that's how I know. You can kind of tell it's fake because of what people have put in it. So yeah, people test all different kinds of things like participating media. There's another model out there where they've kind of added extra like these drapes and all sorts of stuff because it adds a lot more complexity to it. Yeah, so yeah, Mitsuba, they have so let's see here. I'm seeing the Lucy model, but let's look at the documentation. Here we go. I'll let this load. That I'll just search for it. For some reason, it doesn't like showing up right now. Okay. Anyways, it looks like this, but they do it because they can kind of have like it has an outer shell to it and like an inner shell, so you can kind of test different materials on the inside and on the outside and kind of see how it responds. So, and the teapot's also kind of useful because of the fact that you got that loop on there, so that causes issues with some rendering stuff because for one, it's going to cast shadows. It's not convex, so a lot of these 3D models are kind of chosen for particular reasons. This one has like another like shell in there, so if you're trying to simulate like inner reflection, in order for light to kind of reflect around on there, it has to kind of bounce around. Okay. So let's see here. How about I stick with the Mitsuba model for now? That sounds good. I'll stick with the Mitsuba model. And then what we could do is test the
can you please explain the vertex shader also?
Yeah.
.bar.
Yeah, let's take a look at that. So let me load up. We're gonna need
that object you are loading, .obj, is it something we are downloading and then uploading here, or is just looking at the name?
Yeah, so the actual those models are located with the libxor, so if you want to use it, you can just copy it, or you can copy it out and use it. And there's no issues sharing it, using it. They're all public domain 3D models, so that's why they're also popular, is because anybody can do anything with them. They're not like, oh, you're stealing our 3D model and using it for whatever purposes. So okay, so yeah, so let's just go ahead and see what happens. Okay, so inside the vertex shader, we have our uniforms, which these are like constant values that we set for the entire shader. So the projection matrix, camera matrix, world matrix. And then we have our 3D attributes that are coming in, so the position, normal, texture coordinates, color. And then varying, these are our outputs. Okay, so these are going to have to match the fragment shader. So if you'll see inside here, we have, oops, we have exactly the same thing. So one easy way to do it is just make sure you copy and paste those.
And what about the attributes? Like, those are not constant, right?
No, those are our vertices, essentially. So each of the vertex model, so just as a way of seeing what's happening underneath. So let me minimize this. And there's a class called index geometry mesh, which if we take a look at this, skip some of this. Okay, so So inside this index geometry mesh, we have I have an array to hold the vertices, the indexes. So what we're going to do is we have a 3D model. We could, for example, an icosahedron. So an icosahedron, you could have these three rectangles at right angles to each other, and they're really the golden ratio. So this is the golden ratio, and that's 1. So the ratio of the size. Okay. So we have this. Try and draw it correctly. And then we have another flat one. Okay. So these are all kind of going through it. All right, so if we wanted to kind of draw this mesh out, we could maybe that's just too complicated. Let's just go with the square. The marker is too thick. So so we can have a cube, right? So we're going to have 8 vertices. Okay, so there's 1, 2, 3, 4, 5, 6, 7, 8. So we have 8 vertices. And then in order to draw this out, we have a bunch of squares here. So we have 6 squares, but let's just call, we'll just say we can draw squares. All right, so we have a vertices 1, 2, 3, 4, 5, 6, 7, 8. But now instead of repeating the vertex information, we can index it. So we could say that the one facing out here is 1, 2, 3, 4. So that's polygon 1. And then polygon 2 is 4, 3, 7, 8. And then the back one would be 8, 7, 6, 5. Okay, and so on. So we can do this for each of these sides, but if we had to spell out each one, like, we'd have a bunch of duplicated information. So there's 6 polygons, but because that would be 24 copies of the vertices. So if we index these, then we can kind of compact it out a little bit, so we're not reproducing. I guess it gets the memory footprint lower, because a lot of times you have shared vertices with a bunch of polygons around it. So same idea here. We have the vertices and indices and surfaces. Basically, a surface just means that we're going to draw a particular kind of shape. So they could be like triangles or lines or points. And then we have these buffer objects. So this is the actual memory buffer we're going to stick this stuff in. So this is, we can tell the 3D library that, okay, we're going to stick some raw data. And this is where the attributes come from. Okay, so what we're going to do is every time we draw a vertex, let's see here. Like, for example, if we wanted to draw a rectangle, then we would say, hey, let's start like a triangle fan. So we set the normal, set the texture coordinate, set the position, and every time we do that, then I basically just append, every time we append, then I basically just copy the current vertex, which the vertex is a structure that has the position, normal, color, and texture coordinates. So you see this kind of matches what I have in the shader. So I have decided that I'm just going to kind of make that all my shaders are more or less going to follow the same format. Otherwise, you have to kind of manually say, I mean, you can make it say whatever you want. You can say my memory buffer is laid out position and then the color. Maybe you just want positions and colors, or my memory buffer only has the position, the texture coordinate, and the normal. And so you can kind of detail how you want to lay that out in memory. So inside here, so in the vertex shader, we're basically saying, okay, this is what I'm expecting. This is what the shader is expecting. And inside of the, where's the, okay. So then when I go ahead and create those memory buffers and I copy everything in it, then I can say exactly, okay, so like over here, the vertex attribute pointer, we got an XYZ, so it's 3. They're all floating point numbers. The stride, so they're all laid out sequentially, 48 bytes of data, because a float takes 4 bytes, and we have 12, so 4 times 12 is 48. So they're all 48 bytes apart, and minimize this. Okay, do this go faster. Okay, and then we have our offsets here, and the offsets are going to be, the position is at offset 0, and then 12 bytes later we have the normal, then 12 bytes later we have the color, or the texture coordinate, and then 12 bytes later we have the color. Okay, so we basically have, so there is a step where we basically say, here's what the memory buffer is going to look like, here's how all of these different attributes are laid out in memory, and then our vertex shader matches that. Okay, so other 3D programs will have something similar where you might have to say, or they're a lot better, like because they're much larger libraries, they can like enumerate, okay, this shader has these variables in it, and they can kind of do all the matching. But if you want to keep it simple, right, and have a small code base, then you just have to say, well, we're only doing it this way. Yeah, so that's where those attributes come from. So those are the vertices. So in the case of this cube, this vertex shader is going to, as we're going through, it's going to be called on 1, 2, 3, and then 4, and then 4, 3, 7, and 8, 8, 7, 6, and 5. And it can be smart to some degree and say, I already calculated 4, I'm going to reuse what it already got. So there is some scheduling that kind of goes on so we can make sure we don't duplicate calculations. Does that answer the, yeah?
Yeah.
Okay.
Because when I was trying to see all those files, I was not finding like, okay, we are initializing those, but what's the value? I mean, how is decide the values?
Right. How do we know that there's 4 of them and they're called A position, A normal, A text chord? And
I mean, in Fragment Shader, you can just right click on any of those, it just go for the definition.
Yeah.
But here, it's not like that.
Right.
Yeah.
Yeah, and you see over here, if I go back to index geometry mesh, this is where I have hard coded those values in there. So position, normal, color, texture coordinate. So there's the offsets there, 0, 12, 24, 36. So I've already kind of predetermined that's an ideal way of doing it. So because it's going to handle most use cases that I have for it. I just want to put a 3D model on the screen. It has texture coordinates. It might have colored vertices. It might have the normals associated with it. And for most of the things that I'm going to want to do, those are all that I need. If it was more advanced, like if you're doing animation, you may even have extra information in there to kind of support that. So, but yeah, so it all comes down to that initial design, but that's where they come from. It's basically, I decided that's what I'm going to have. That covers most things I need for now. Maybe in the future I'll say, okay, let's go ahead and add some more. But for now, that's where I'm at. Okay, so the attributes, and in later versions of OpenGL, they changed those so that attribute is just in and varying is out, which, that makes more sense. But because WebGL is based off of an earlier specification of OpenGL, that's just the way it is. So, so we have to use those. Okay, so then all I'm doing is multiplying the world matrix by the position, and we get rid of the W coordinate. So if we set W to 0, then it treats it like a vector, and then I just copy whatever the attribute, whatever vertex color I said, just pass it on to the next one. Same thing for the texture coordinate. We're not doing anything special, although if you wanted to, you could do some kind of special function in the vertex shader. The nice thing about it's all programmable, so you can decide to do whatever you want. Okay, and then over here for P, this is we're calculating the position, and the reason why that I do this separate from just doing it down here is that I want to save the vertex position for later. Okay, and then once I've saved that, then we go ahead and calculate the final position. So projection matrix times camera matrix times the world position. So then inside of our fragment shader, we have a few more. These are kind of made so they match so the OBJ format has a corresponding material format file. And so it'll define things like we can say, okay, we're going to apply a red material, or we're going to apply a texture map, or different things in there. So this one program called Alias Wavefront, this is where it all kind of comes from. They had this text format you could save out to, and just so you can see. I mean, Alias Wavefront is essentially the software that became Maya. So have you heard Maya? Yeah. So back in the 90s when they were doing, it was called Alias Wavefront, and that file format has stuck because it's so simple. In fact, if we were to take a look at a box, so let's take a look at the box. You'll see here this says, okay, we're going to use this material file that has our materials in it, and over here we can see, hey, there's our vertices, so we can it's just an easy to read texture format. There's the normals, so we have 6 normals pointing for each side, 8 different texture coordinates, and then over here I'm going to create this G stands for a group. It's like a smoothing group. So then we're going to use a material named box. And then these are our faces. So this first one says use vertex 1, use, I think that's texture coordinate 1, and this is normal 1. Okay, and just to kind of save, this one says, okay, this polygon, and what you'll notice here is that for this first face, right, we divided our square into 2 halves, and they all use the same normal, which is sticking straight up. Okay, so that's the top of the box. I can tell it's the top of the box because of the way it's pointed. Okay, so you can see it's a very simple format, and nearly everything exports out to this format. So that's one reason I like it. The second part is the box. So the material. So over here, I'm creating a new material called box. This is a specular exponent. D is the transparency. So I think they stands for diffusion, or how transparent it is. So 1 means it's solid. TR, I think that has to do with reflectance or transmission. So D is 1, TR is 0. So in other words, how much gets transmitted versus how much gets reflected. So the same number, basically, just a different way of looking at it. Okay, so these ones down here, I mostly ignore this stuff. I have a few that I want, like the KD is normally the color. KS has to do with the specular reflection, so how much light. So if this was gold, you'd probably set the specular color to gold. So anything reflecting on it gets kind of gold tinted, you know. Or in this case, it's just like a lower version of white. So in other words, they don't reflect everything, just 35% gets reflected. And then over here, I can say, let's use this texture map. Okay. Which I don't have this texture currently loaded. But if I did, then this box would basically have a texture map associated with it. These other ones also, like the Mitsuba one, also has, you see there's two materials. One's called Mitsuba Inside, one's called Mitsuba Outside. And they're two different colors. So this one's like black, because 0.01, that's almost black. And then this looks like it's probably kind of like a gold color. And there's no textures on the outside material, and I have a texture on the inside. Okay, which all I did was copy these objects over, so we're not going to see any. I guess I could add the textures, unless I already have them. No, I have a few. Let me copy those textures because we're going to want them. I know I'm going to want to use them, so let me go to the previous class where I took these out of. Oops. Wrong one. Textures. Okay, I'm just going to copy all that. There we go. That might not do what I'm expecting. I might have to move all those to a, or I might have to move the models into a, yeah, it's possible. Let's do that. Okay. So if I go here, I hit refresh. Okay.
For this one, so when you write something in your .html file, is this the light server you're using or light server?
Light server.
LITE?
LITE-SERVER. And it's one of the libraries that gets installed with Node. So once you've installed Node.js, then...
What is light server? So I did show something like light server.
Oh.
You're still like working, but I was just confused. Like, is it light server or light server?
Oh, yeah. No, yeah, light server.
Okay.
Yeah. Okay, so let's see what we can do with this in the meantime. So we got our fragment here, right? So if we wanted to, we could throw in like the position. So maybe we could see what the position looks like. Now, this is probably the colors are going to be yep, I think that looks fine. So you'll notice we have different colors than the normal because the well, they'll be pretty close, but more or less we're just using the actual normal to kind of say what the color. We're basically just using the 3D position data as an input for the color. But if we wanted to kind of say, well, what if we used the Z? So let's try that out. Okay, so, oops. This will make it white. And let's try and color it as if we're using the Z coordinate.
So when you write like that, big 4 and then just 1, then all the 4 values will be 1?
Mm-hmm. Okay. So there's the Z value, but I think there's a... I'm going to see if this works. There's some special variables in there, and I think frag chord is the... Oh, okay. Here's a helpful tip. Because we're multiplying the Z by the alpha value also, we're basically like killing the alpha value too. So let's... Come on. Everything's running slow. Okay, so now when this reloads, so that's... Got to do a little bit at a time. Okay, I'm trying to scale the Z down. Oh. So in that case, now it looked like it was giving X and Y, but that it wasn't giving the... Okay, now it looks black. I was thinking. Okay, that's better. Okay, so you can kind of see the fry coordinate kind of gives us some information. All right, so that would be like another component on the gbuffer is our z coordinate, so the depth. So that kind of gives you maybe a visualization of what it looks like when it's recorded inside the depth buffer. And you notice that everything else around here is just transparent because we're not drawing anything there. So in the depth buffer, all that would be 1.0. That would represent the far. Yeah, as we looked at. Okay. So now that the next part is like applying some kind of light, right? So if we were going to just use our color or input color, first of all, let's see if we got anything on our KD, which is normally so that's 0. So right now that's black, but if we were to go here and set a color, so if I said rc.uniform 3 and so this should set it to red. So when this loads up, well, let's see. Okay. We're expecting a
the hardest parts the bottom. On the bottom.
Okay, I just have to be patient. Okay, so there it is. So we have red. And then we also need, let's put something for our sun. I think I call it sunder too. And this is going to be let's just make something up. So now if we have like the our n.l lighting, which is kind of part of the rendering equation, right? So we could take the dot product of n and l, and what I like to do is we'll say that n equals we want the normalized version of our vectors. Okay, and so once we have n.l, then let's go ahead and multiply it by our color. Okay, so now you can see that we have, we can kind of apply some lighting to our real-time model inside the shader. And however, I will note that we did n.l, but those are negative values that we're trying to write. Again, they get clamped between 0 and 1. So normally we have to take, and just to kind of show you that that is the case, I'm going to say that we'll take half of n.l, and you'll see that it goes from, it'll still go smoothly from 0 to 1. So that's a problem, okay? So that's why we put the angled brackets on the Renner equation, because we're saying let's take the positive dot product, okay? Positive dot product. So here's what I like to do. I like to do this. Max of 0 and the dot product. So what happens here is that if the dot product is less than 0, then we just return 0. So this has the effect of clamping it down. So let's see if this is actually. So now what you'll notice is that instead of it going smoothly from 0 to 1, it's clamped at half. So that shows you that it actually did what it's supposed to do. Whereas before it was smoothly going from black to our full range color. So now, because what'll happen is that you're normally summing the contribution of different lights. So you might have the sun, you might have some point lights. So what's going to happen is that if you don't take that positive dot product, you're adding, you have negative values in there, and then when you're trying to add a light, it's just offsetting a negative value when you want it to be offsetting 0, if that's what it was. Okay, so this was one of our main vectors. So yeah, that looks like it's doing the trick. And yeah, so that's how you kind of add basic n.l lighting. Now the normal is being applied, so those are all world coordinates. So we have our view vectors kind of moving around. The other value that we could have is called, we'll just end with this, is the camera position, okay? Which I think that we want to, we might, I'm thinking we normally bring this in as a uniform variable for the whole thing, just whatever the direction of the camera. But we could also just, we could add another inside this one. The camera. And then now what we could do here, we could take the fourth column of the camera matrix. And let me just see if this is going to work for us.
So when you write something with carrying this thing and then dot xy or something, but it's like xy0.
So that's a fast way of getting the components in the order that you want, because inside the register, so you just think of the register file on the GPU. It's storing X, Y, Z, W. So if you wanted to access just, say, this component, for this component, then we would say, okay, that variable dot x. So we kind of treat it like an object. But we could also do some other things like swizzling. So let's just say we have a vec3, okay, equals something. We could say p.xz, and that would return a vec2 with x and z in it. So it's kind of cool. So internally, it looks like that. But they also have other names, so you could actually call it, you can refer to it as RG, B, and A, and S, T, E, and Q. So if you're, so these mean the same component in the register or inside that object, but if you're doing texture coordinates, a lot of times S, T, P, and Q are what you use. If you're doing color, R, G, B, and A, positions or vectors, X, Y, Z. Okay, yeah, and so this last one we were doing is the view direction. So, which I'm gonna just double check and make sure, because I just kind of am guessing we basically just want to say, because in those lighting calculations we've got the hemisphere, so that's the normal, that's the light, and we're going to need the view vector as well in order to do other calculations. So these are the main values we're trying to get out of there. So okay, so that'll be that for now.